Hi there. So let us start Bend's rule in covalent molecules. This is the 18th lecture, Bend's rule. This is an alternative to VSEPR theory. It's a very interesting rule. It says that the atomic S character concentrates in orbitals directed towards electropositive substituents. Conversely, the atomic P character concentrates in orbitals directed towards more electronegative substituents. I'll explain to you. Now, we know in the p block elements where the central atom undergoes sp2, sp3, sp hybridizations. If the hybridization is sp3, we say 4 equivalent hybrid orbitals are formed. If it is sp2, we say 3 equivalent hybrid orbitals are formed, and so also in sp2 equivalent hybrid orbitals are formed. So in SPN, in general, in SPN type of hybridization, we have n plus 1 equivalent orbitals. Those are associated with the central atom. That is our feeling so far. But Bend said no. Yes, the central atom is using hybrid orbital. He didn't deny. The VBT concept is acceptable. But the hybrid orbitals are not all equivalent. Yes, if the molecule structure is symmetrical, equivalent symmetrical, for example, methane, all the peripheral atoms or the ligands are same, hydrogen or CCl4 or CF4 or BCl3 or BCl2. If the symmetrical molecule we are talking of, then yes, all the hybrid orbitals are equivalent. But if the structure is unsymmetrical, supposing CH3F, CHCl3 or CH2Cl2 or CHCl3, then the different hybrid orbitals, may it be 4, may it be 3, may it be 2, they are not equivalent. They have dissimilar S contribution and P contribution. I remind you, in sp3 hybrid orbital, we calculate 25% S character and 75% P character each possessed by each hybrid orbital. In sp3, 33.3%, sp2, 33.33% of S and 66.67% of P. And in sp, 50-50. But in Bend's rule, we will find that the contributions are not equal. If the atoms are not equal, if there is a lone pair, then the S contribution, P contribution in the hybrid orbital, they are not same. Non-equivalent hybrid orbitals. Therefore, atomic S character concentrates more towards the orbital which is more electropositive or less electronegative. That should be better. In my language, it should be less electronegative. In the language of Bend, it is more electropositive atom or substituent or ligand. For example, if you look to the actual bond length, bond angle of CH3F, methyl fluoride or fluoromethane, you will be surprised. No VSEPR theory will help you to explain. So Bend rule came to our rescue. See, the CF bond length is convincingly more, 1.38 angstrom, while the other 3 CH bond length 1.09 angstrom. Yes, this is understandable because H is a small size than fluorine. That can be rationalized from the size of the ligand atom. But what about bond angle? This bond angle FCH bond angle is less than tetrahedral, 108.7, while this HCH, this, that is more than tetrahedral, 110.5. This is 108.7. So how to explain the different bond angles? It's not methane, but all bond angles are 109.5 degree. In this case, the CFC bond angle is less than tetrahedral and the CHC, HCH is more than tetrahedral. This can only be explained by Bend's rule, which says that yes, carbon uses sp3 hybrid orbitals, but since hydrogen is more electropositive or less electronegative than fluorine, so the hybrid orbitals used towards hydrogen will have relatively more s character than the hybrid orbital used in the direction of fluorine. Conversely, the p character in the hybrid orbital in the direction of fluorine is more. So here we have two generalization. More is the s character in the bond, stronger is the bond, and shorter is the bond length. We have already known that more is the s character, shorter is the bond, stronger is the bond, shorter is the bond. And because of the greater s character, the bond pair repulsion will be also more. That will make the bond angle more. That is the reason why, since these three CH bonds have greater s character relatively than this, so there is a greater repulsion between these three bond pairs. The bond angles is exceeding tetrahedral, but because this has more p character, so the repulsion factor is less between this, right? Because there is a p character, more p character. P electron density is smeared away from the central atom, so the repulsion between this is less. So the bond angle is less than the tetrahedral angle. And the same reason will tell us that the bond is stronger. Bond energy also, this CH bond energy is greater than the CF bond energy, that we know. Bond energy data we know, CF bond energy, that is the only exception we found in case of single bond category, right? Because of the polarity factor that we know. But that was explained by Hooke's law. The bond energy was greater. That cannot be explained by this Bend's rule, because in that case, if more is the p character, this would have been the weaker bond. And we have seen this, it is very, very fresh in our memory. CF bond energy, CF is 485, while CH is 413. Convincingly, CF is greater here, very close. And so there you cannot bring in Bend's rule to explain that CH is a stronger bond than CF. Well, bond length and bond angle, they can be well explained by Bend's rule in case you fail in BACPR. Then we had another NB, non-bonding electron pair, NBEPR theory, the ligand-ligand repulsion theory. Now we have Bend's rule mostly for bond angle and bond length, not for bond energy, right? We have different weapons at our hand. To explain the observation, we can use any weapon, suitable weapon, logically to explain. If this weapon is valid for the bond energy, the other weapon can be valid for the bond length and bond angle, right? This is mostly for bond energy and bond angle. Bond length and bond angle. Now, see, this is a very interesting case. How to explain without bringing in the Bend's rule? You can't explain at all. This is dimethyl ether, methyl. The bond angle is more than tetrahedral. How to explain? When the steric number is 4, the bond angle is tetrahedral, and there is a lone pair, the repulsion is expected to reduce the bond angle from 109.5, but it is instead it is greater. And in methanol it is close to tetrahedral, and in water it is less, and in OF2 still less. In OF2 still less, 103.8. Can you believe? It is still less. What makes the lone pair bond pair? There are two lone pairs in all these cases. Then why this bond angle is so less? Now before we apply Bend's rule, let me tell you that CS3, you have not studied perhaps organic chemistry, you cannot understand, but to make it more simple in my presentation, let me tell you an alkyl group, methyl or ethyl, it has got more electropositivity. It is more electropositive than even hydrogen. Methyl or ethyl or any alkyl group is more electropositive than hydrogen. Because you will know it has got an electron releasing nature. That is called plus I effect. Inductive effect is positive. It pushes electron away from itself. Because of that electron pushing, electron donating nature, this alkyl group has greater electropositivity, more than hydrogen. So this thing you must learn now, the methyl is more electropositive than hydrogen. So more is the electropositivity according to Bend's rule, more is the S character. So these bonds created by the hybrid orbitals, sp3 hybrid orbitals of oxygen, possesses more S character, maximum S character. So more is the S character, more is the repulsion between these adjacent bonds, and more is the bond angle exceeding the tetrahedral angle, because methyl group is more electropositive than hydrogen. So as one methyl group is replaced by hydrogen, then the S character is reduced. Here there is same S character, this is methyl, but here methyl is more electropositive, hydrogen is relatively less electropositive, so the S character becomes less, so the repulsion becomes less. Therefore the bond angle is reduced to more or less tetrahedral. And here in water, both the methyl groups have been replaced by hydrogen. So the S character is still less, comparative, in a comparative manner we are discussing. And as a result, the bond angle is still less. Let us not talk about BSEPR at all. Talk about Bend's rule. How the bond angles, it is going below tetrahedral because the S character is, less. Of course, compared to fluorine, supposing this is OF, again fluorine is much more electronegative than hydrogen. So the P character will be more, S character will be still less. So more is the P character or less is the S character. The repulsion is less. Hence the bond angle is also less. So that explains why OF2 has the minimum bond angle even much lower than the tetrahedral angle, and dimethyl ether has a greater bond angle than tetrahedral. Only this BSEPR theory cannot explain. Only Bend's rule can explain. Right? And one more interesting thing about the lone pair. How to explain the importance of lone pair in Bend's rule by bypassing the BSEPR theory that the lone pair bond pair repulsion is more than the bond pair. This we won't use now. We will use a different concept in Bend's rule, the S character, P character in a hybrid orbital. Right? Now let me read out. A lone pair in a hybrid orbital is considered to have maximum S character. Remember this is the presumption in Bend's rule. If there is a lone pair in an hybrid orbital, occupied, not unoccupied, occupied, not bonding, non-bonding, then since it is, it's not being shared with other atom, it is bound close to the central atom's nucleus, so it has got more S character. So the S character is maximum in a non-bonding occupied lone pair orbital. That is the presumption. So if you compare between ammonia and water, why the bond angle is a few degrees less than tetrahedral in ammonia and many more degrees less than in water? It is because ammonia has one lone pair in nitrogen, while methane doesn't have. So the presence of lone pair in nitrogen atom consumes more S character, because I told you that the lone pair orbital consumes more S character. That is the presumption. So if S character is smeared or is consumed more by this lone pair orbital, then the S character relatively becomes less in this 3 NH bonds. So the repulsion is less, bond angle is less than the tetrahedral. And if there are two lone pairs, the S character is being squandered away, is consumed more by these two lone pairs. So the remaining S character left out for these two OH-OH bonds will be still less. And therefore the repulsion is less, bond angle is still less. So we can explain the lone pair eating away more S character in the hybrid orbital, so that the remaining S character being lessened in other bond pairs, other bonding orbitals. Now another question, it's a very interesting question, ammonia compared with NF3. Yes, about polarity you have already known why this is very weakly polar than ammonia, that you know. Taking polar dipole moment as a vector quantity, you know that. But I am asking the bond angle. In ammonia it is 107 approximately, and it is 102 in NF3. How to explain? How to explain this? It can be best explained by Bend's rule, because hydrogen is electropositive, fluorine is electronegative. So the hybrid orbitals, sp3 hybrid orbitals used by nitrogen will possess more p character towards fluorine, more s character towards hydrogen. Of course S character is 25, but little more, maybe 30-70. But here it will be 20-80, 80% p character. So more is the p character, that means less the S character, less is the repulsion between these bonds, and less is the angle. So that can explain why NF3 has a smaller bond angle than ammonia. Now I have brought a very interesting example for you to compare. Now this is an organometallic compound. This is dimethyl dichloromethane. Dimethyl dichloromethane. C connected with 2Cl covalently and 2-methyl. This is carbon-carbon bond, this is carbon-chlorine bond. And the measured angles are between chlorine atoms, the bond angle is 108 degree approx. And between methyl-methyl, the bond angle is 113, more than the tetrahedral. This is less than the tetrahedral. You can explain in the same way, because chlorine is more electronegative and methyl is more electropositive, more than hydrogen. So the S character concentrate more here in these two bonds. Repulsion is more, so angle is more. Here more P character, so repulsion is less, the bond angle is less. One exceeding tetrahedral, one decreasing from tetrahedral. Same thing happens, but the angles are different. Same trend you find in silicon compound, dichloro, dimethyl silane. Same, this is exceeding tetrahedral, this is decreasing tetrahedral. Same thing you find plumbane, dichloro, dimethyl plumbane. So this is 134, this is 101. You cannot explain this by ordinary VSEPR theory. If you include the Bend's rule, you can explain well. Now I have another interesting example for you. Do you know that in a trigonal bipyramidal geometry, basic geometry is trigonal bipyramidal, where there are three bond angles. One is the equatorial bonds 120 and the axial bonds 180, and between the axial and equatorial 90. But if there is a lone pair, then it will change. How to explain this? For example, we take sulfur tetrafluoride. The steric number is 5. There is a lone pair here. There is a lone pair here. Now the steric number is 5, and the hybridization is sp3d. I have written it here somewhere. Right? But one of the lone pairs have to be put in an equatorial position so that the repulsion factor is minimized. So if you do so, then the actual bond angles becomes different. In the trigonal planar, this equatorial bond, CFF bond, is only 101 instead of 120. Expected angle is 120, it is 101. And the axial bond is expected 180, it is 173. How to explain this? Explain on the basis of lone pair. Lone pair will eat away more S character, leaving less S character, that means more P character to these SF bonds. And because of more P character, the repulsion is less, so the bond angle is less than expected 120. And here also it is less than 180 because the repulsion is less. Rather, this will push on this side, the bond angle is more than 90. So 360 minus 173 will be greater. So this angle will be more, but we are not interested in this angle. We are interested in FSF angle in the axial positions. It is 173. And very interestingly, when it is replaced by an oxygen, this is SOF4, sulfur oxytetrafluoride. There is no lone pair, but still it is sp3d. Steric number is still 5, but the bond angle is little more. Why? Because it was lone pair which was consuming more S character, but there is no lone pair here. So the S character in all the SF bonds becomes more compared to this. So as the S character comes more, so repulsion more, bond angle is more, but still less than 120. Because F between F and O, F is more electronegative, so the P character is more, repulsion is less. So bond angle is still not 120. And since oxygen is less electronegative, so more S character is there here compared to others, there will be more repulsion to these bonds. So these bonds will be further compressed to the other side so that this angle becomes less than even 173 to 164, because oxygen is relatively less electronegative. So the S character is more, so that will have a greater repulsion between the more P character SF bonds and will compress more. That explains nicely, more convincingly, to the observed bond angle. And let's talk about bond length. How Bend's rule comes to our rescue to explain the bond lengths. Just think of the CF bond lengths in substituted methanes. This is fluoromethane, difluoromethane, trifluoromethane, tetrafluoromethane. And it has been proved beyond any doubt that the bond length goes on decreasing. In monofluoromethane, it is 1.388 and it goes on decreasing, and in tetrafluoromethane, it is 1.323. It is the minimum. Why the bond length is minimum? Because if you go in this way from bottom towards top, it will be better for your understanding. Now in CF4 being a symmetrical molecule, the S character is 25% in each CF bond. But as more and more hydrogen is substituted, S character is squandered away, is hijacked more by the hydrogen side. So less S character will be found in the CF bond. So less S character means the bond length increases. More S character, bond length decreases. Less S character, bond length increases. And if there are two hydrogen atoms, S character is eaten away, is hijacked more to the two CH bonds, and till less S character, more P character will be found in the CF bonds, so that bond length becomes still more. And finally, most of the S character is taken away by the three CH bonds, and the CF bond has the maximum P character, so the bond length is maximum. Same trend you find in case of monochloro, dichloro, trichloro, tetrachloro, methane. Tetrachloromethane, it is the smallest bond length. We are all talking about CCl bond. All are CCl, but they are different. That's the interesting thing. We are not comparing CH with CCl or CH with CF. It's not that. We are comparing CCl for all these chloro derivatives of methane and CF and all the fluoro derivatives of methane. This can be explained by Bend's rule and Bend's rule alone. Greater is the S character, you can say stronger is the bond and shorter is the bond. And bond angle will be more, no doubt, because of greater repulsion. Now, there is a limitation. Bend's rule cannot be used everywhere. There are limitations. For example, when there is a prominent NBEPR, when the central atom is small, second period element, and the peripheral atom is third period element, bulky, there is a steric repulsion between the electron cloud in space. That EPR will come, that will completely destroy Bend's rule, and the bond angle becomes more than tetrahedral. Even if the steric number is 4 and there are two lone pairs, BS-EPR will say the bond angle should be less than tetrahedral, but actually it is more than tetrahedral because of NBP-EPR. The ligand repulsion because of greater size, right? And also in some transition metal compounds, Bend's rule cannot be applied. Many transition metal compounds, because transition metal, they use their d orbitals. N-1 d orbitals, they are of lesser energy than Ns. Ns orbital was of higher energy. But in P block, Ns was higher energy NP was higher energy and Ns was of lower energy. But here, N-1d is of lower energy and Ns is of higher energy. That's the reason why the trend is opposite. And Bend's rule is not valid for explaining the bond angles and bond lengths in these compounds. For example, titanium, group 4. Titanium, dimethyl, dichloro, titanium dichloride. Dimethyl, titanium dichloride. The opposite here, towards the methyl bond angle is less than tetrahedral, and the chlorine bond angle is more than tetrahedral. Exactly the opposite what we found in other main block elements, main group elements. Why? Because it is d orbital which takes part, which has got a lower energy than the Ns. Now, interestingly, if you apply the concept of hybridization, it is not sp3, it is sd3. Or other D3S hybridization. D3, N-1 D3 and S to make it a tetrahedral molecule. In that case, the S character concentrates towards the more electronegative atom, just the opposite. So if the S character concentrates here, then the bond angle becomes more in more electronegative ligands and less in more electropositive ligands. So we are not saying any Bend's rule, but I am just saying why the opposite thing has happened. It may be due to that the d orbital has a lower energy than S, N-1 d is less than Ns. That's the reason why opposite thing might have happened with respect to Bend's rule. Now, these are a few examples, right? Now, how Bend's rule can be used to explain the bond angle in water, in OF2 and OCl2. We should call Cl2O. In reality, it should be called dichlorine monoxide, not oxygen dichloride, because conventionally, the less electronegative element should be written first, then the more electronegative. Doesn't matter. This is a copy-pasted thing. thanks to Google. Now, explain the bond length can be explained because the size, they are different. Size wise you can explain the bond length, but bond angle, explain the bond angles. The correct order is OF2 is the minimum, is 104.5. This is OF2, this one, I'm sorry. And water, it is 104.5, and the maximum exceeding the tetrahedral is OCl2. This doesn't come under bent. It comes under NBEPR. NBEPR, when the central atom is small, that is second period element, and the peripheral ligands are third period or fourth period, then ligand repulsion will make the bond angle greater than the tetrahedral, although the hybridization is sp3. There are two lone pairs, not so. But these two cases can be explained. We have already done that. Fluorine is more electronegative than hydrogen, so S character is more here. That makes the repulsion little more, and this is more electronegative, so the P character is more here, the repulsion is less, so the bond angle is less. Bend's rule can be applied, but here it can't. Now, let us try to apply all our knowledge, including NBPR, to explain why chlorine dioxide and chlorite ion and dichlorine monoxide, which we have already discussed here, and grade them. And we found that chlorine dioxide has the maximum bond angle greater than tetrahedral, and chlorite ion is also greater than tetrahedral, and dichlorine oxide also greater than tetrahedral. This has been settled, already settled, NBEPR. But here the central atom is bulky, right? And the bond angle will not be tetrahedral, it will be more than tetrahedral. It's very, very difficult to explain by Bend's rule here. This is NBPER, but in the other two cases, the third period element is bulky due to its large size. The bond angles are greater than tetrahedral. Bond pair repulsion, there are, you have to bring in the bond pair repulsion here because there is a pi bond here. Even if for steric number you calculate 4, hybridization you can say it is sp3, but still there is a pi bond. Another pi bond here in ClO2, there is a greater repulsion factor here. As a result, the bond angle is more. And here there is a single bond. Of course, there is a resonance, the bond order is 1.5, here 2. So there is definitely less repulsion and bond angle is less. But more than tetrahedral in both the cases because the bond order is more than 1. In both the cases, the bond order is more than 1. Here the bond order is 1 and 1 each. So here, interestingly, chlorine dioxide is a paramagnetic molecule. 1 unpaired electron is there. That also contributes to, lessening the repulsion. And there is a pi bond. Both are pi bonds. They will repel more. MOT has clearly explained the situations in ClO2, the paramagnetic behavior, or else we were doing 3 electron bond concept. That I have not shown it here, made it simple, kept the unpaired electron in a different orbital. This chlorine can expand its valence shell. So I have nowhere brought the Bend's rule to explain this. My hands are tied, but I explained on the basis of bond pair repulsion. Here, the lone pair repulsion factor is there. Here it also is there, but there is 1 unpaired electron. Repulsion is less, and moreover there is a pi bond. Bond order is more, so repulsion factor is more. And this is NBPR, that exists. In all these cases, the bond angle is more than tetrahedral. And to finish, to say thank you before I leave this, there is another interesting example. Dimethyl oxide, or we can call it dimethyl ether in organic language. This is diacetyl ether, right? So you find in diacylyl ether, the bond angle is 130, while in dimethyl ether, it is 111. Both are greater than, there are two lone pairs. One will expect sp3, but the bond angle is more because of Bend's rule. This is more electropositive, more S character, bond angle more. But SiS3, silicon, is more electropositive than carbon. So SiS3, the silyl group, even has a greater electropositivity. So compared to methyl, silyl will have this direction more S character by the hybrid orbital of oxygen. So repulsion factor is still more, and it is therefore 130 degree. Moreover, I told you, if you have not forgotten in your bonding program, that there is a possibility of the d pi p pi back bonding, the vacant d orbital of silicon, which it has, and one of the lone pair orbitals, occupied orbital. They go for a collateral overlapping, the d pi p pi back bonding, that makes the hybridization status changing from sp3 to sp2 to some extent, for which also there is a change in bond angle, right? And last but not the least, to compare, it has nothing to do with the Bend's rule. I've just given for a sake of our brush up. NO2 plus, NO2, simply NO2, which is a paramagnetic molecule about which we are talking. We are talking about ClO2. This is NO2, again paramagnetic. And this is NO3 minus, nitrate ion. Nitrate ion, this is the anion of nitric acid. And this is nitrite ion, the anion of nitrous acid. The bond angle, this is 180, exactly linear because this is sp hybridized. So no anomaly, nothing. And this is 134.5. Now there is one unpaired electron, so the repulsion is less, is expected to be sp2 120, but the repulsion factor is there is, the pi bond is there, so repulsion bond pair repulsion is more, and from the lone pair repulsion is less, so the ultimate bond angle is 134.5, more than the expected 120 degree. And it is exactly 120 degree because there is lone pair, no unpaired electron here in nitrate ion. But here there is a lone pair that will have a greater repulsion. And even if the bond order is 1.5 because of resonance, because of the lone pair bond pair repulsion, and the hybridization is sp2, so there is a slight decrease in the bond angle, 115 instead of 120, right? So we can apply Bend's rule in nitrogen dioxide. The S character is less in orbital containing one unpaired electron. We can say yes, we can apply Bend's rule, because if there are two electron pair in a in a non-bonding hybrid orbital, then it will consume more S character. So one unpaired electron will consume less S character. So more S character will be distributed among these bonds. So the repulsion factor will make it greater than 120, right? So relatively more S character towards the NO side, so greater repulsion than expected. In nitrite ion, the lone pair, this one particularly, the lone pair consumes, we can apply Bend's rule. The lone pair consumes more S character, so the S character is less here. P character is more, so the bond angle is less. So we can apply Bend's rule. We can apply also BSAPR theory to say, wow, the bond angle is less than 120. So in a nutshell, the bond energy, bond length, bond angle, and Bend's rule, how to explain the unexplained bond angle and bond length in some cases. They are thus the approximate rules of thumb, not the exact rule, where the scientists have devised to explain some of the observed results, so that students like you can memorize in a logical manner, course not forgetting the anomalies. Bye-bye. Take care.